Namaskar. So in this lecture we will see about potentiometer. Actually, potentiometer is a device which is generally used to compare the EMFs of different cells or finding internal resistance for a cell which is going to supply you the DC electricity out in the outer circuit. And here the concept in potentiometer is actually a very long wire, or sometimes a pieces of wire. We'll see that how it looks like. But the main idea is that it doesn't draw any current from the cell which is being measured. You can measure the EMF of a particular cell with respect to a standard cell, and also you can determine the internal resistance of the cell. So let's see how a potentiometer works and how we can determine the EMFs or the internal resistance of different cells. So let's begin. So this is a circuit. So as I said, there are two types of circuit. So the circuit here which have the battery system and rheostat, which you can vary the current through it by changing the varying resistance, and there is a key which just connects the whole circuit into circuit. And this is the arrangement. No, this wire, you can see that this is a very long wire, or sometimes it is in pieces of wire where you can see these metal strips which is connected here. They are just connecting one or each other, and there is a this arrangement is compare EMFs for the cells. This arrangement is used where you have a two way switch which is utilized for connecting the cells. So let's say this is one standard EMF which you know, and the one which you want to determine, right? And let's say these are the galvanometer which is connected with this two-way switch, and here the other end you can touch wherever and the wire, and you touch such that again you utilize the Kirchhoff law and the kind of Wheatstone bridge kind of concept where no current flows it. Once no current flows it means then you can determine and you can utilize the Kirchhoff law and utilize the loop rule to find out that what would be the values, and you can have a different equations and you can solve the unknown variables. So for example, let's say this case where you want to compare the EMFs, right, in this circuit. So what you can take in this circuit is that consider this loop here from this to this. So let's say these are the two cells which are connected, and then you can apply the loop where you are just let's say this is connected at position n1 at first, and then you have a galvanometer reading 0, right? So if I take this loop from this point here, which is just let's say connected with this, first you connect the one cell, this loop, let's say that this is the cell connected, this is the two-way switch, so either you connect here or either connect here. So let's say first you connect here, then epsilon 1 is in your circuit, and then you form a closed loop like this through this wire, right? So you'll have something like a stone bridge. So in that case, what would be the current? So here let's say the current would follow from this current would be 0, right, here from here, and this is the resistance, and no, let's say that this is the wire where which is having so uniformity that you can have a per unit length what is the potential difference, and then let's say this is the L1 distance. At L1 this is the point from A, the distance is L1, then the total potential difference between A and 1 will be phi L1, right? So let's say you set it that the potential difference at the length L is equal to phi L1 if this is L1 length. Okay, so it would mean that if the potential difference between this wire is that much, so you'll have phi L1. You start from here, so you'll have a phi L1. And then the current, if I go this direction, right, this direction, though this positive is coming, so I will be taking minus epsilon 1, and then galvanometer reading is 0, right? So it will be equal to 0. Similarly, you just change the switch from here to here. Now epsilon to this EMF, this cell is in the circuit, and then you can have the another point reading where you just keep varying this. This is connected with knife like knob where you can remove this along this wire. So now let's say at this point you get some point n2 this connection, then in that case what would be the potential from A? If the per unit length potential difference is phi, then it will become phi L2, right? And then the similar way you can have a minus epsilon 2, and then galvanometer reading is 0, so you will have a 0 reading. So see, you got two very nice equations, and if you solve these two equations, so you will have a relation like epsilon 1 by epsilon 2 is equal to L1 upon L2, right? So this is a very good relation you got. And now let's say if you know a very well optimized standard, the epsilon 1 is known, then you want to calculate the what is the epsilon 2, then you can easily calculate it to be L2 by L1 epsilon 1, right? So based on this equation, see how nicely you have utilized this equation, and though you have not drawn any current from these cells, and still you are able to measure what is the EMF of the cell, provided you have a known EMF of a given cell which you are going to use here. So this is a one way where you can determine the unknown EMFs for the different cells with the very standard value utilization. That the other circuit uses that for determining the internal resistance of the cell. So in that case, here you have that instead of that two-way box as you just saw here, here we have a register box with the key, right? And this allows you to add this register in the circuit, and then it becomes something like this, right, which we had seen before. So if this is in the circuit R, then you have a V is equal to I minus this, let's say this is your EMF, so E minus I, and if the internal resistance R is R, if the I current is flowing, right? And if it is open circuit, then V is equal to epsilon, right, when it is open circuit. So here again we utilize the similar concept, and the potentiometer would have this this arrangement as it is. And once you connect this circuit, and again you utilize the Kirchhoff rule when following this summation rule, the loop rule here. So let's say in the beginning you have this epsilon connected in the series, and then this circuit will close, and this K2 is open, right? So the current will not flow from here, it will flow from here, and then you apply this rule, and let's say at position N1, this is the length, some length at L1, you are getting this this IG0 here, that current is not flowing for that resistance, because you are again forming a kind of a Wheatstone the bridge kind of structure, right, where it's not actually a Wheatstone bridge, but it's the similar Kirchhoff rule you can apply, because you can form a closed loop where you can avoid the path, this path, because it will have a zero potential through that, right? So now let's say if I go from this path, and at N2, so it will be closing like this, coming back to here. So if you consider this path, then let's say if the phi is that per unit length potential drop, then the total for let's say it is L1 length, so it will be L1 phi, the potential drop here. And if it is going through it, then it will be having -1, because our path is following like this, right? So it is entering it plus, and we have discussed that how to take the sign for this cases. It will be minus epsilon, because the current here entering in the positive and taking out from the negative, right? And in this case there is no resistor, so it would be equal to 0. So it would mean that you have epsilon. Now here epsilon, there is no 2, so I can just take epsilon here. So epsilon is equal to become here your pi L1, right? So this is one equation. Now the other situation is that you close the key. So once you close the key, then this part will become something like this, and then you will have this arrangement epsilon minus VR. And also this is the one equation which will be valid here. And it would mean that if you want to have internal resistance from this equation, then just for this part, so you can write for this R is equal to epsilon minus V upon I, right? This is the equation you can use for finding the internal resistance. So now we need to find out that what is the terminal voltage when this is connected in series, and let's say if this is the resistor box, let's say the resistance is R, then your V it becomes I into R, right? So if you just put that value here, so let me come back to this point again, but before that let me solve this, right? So so once this is closed, then in that case let the terminal voltage between these two is V, right? So V would be what? V would be equal to let's say at this point, now at some point, other point, you are getting the this I00, right? So in that case the terminal voltage would be given as pi epsilon pi L2, right? You have the other length at that where you are getting null, and in that case your you take that loop here from. So between this and this, let's say I am saying that this is a terminal voltage V when you have a resistor box, right? So that voltage will be V, and then you have this cell here in the length between this, so that would be equal to this, because the total closed loop the current would be 0, right? So V is equal to phi L2. So you have another expression. So now we have those two equations. Now we know what is the voltage, terminal voltage V with the relation of this length, and then what is the EMF relation with the length, right? So we can get epsilon by V, and that would become L1 by L2, right? So this is another important point. Now as I discussed here that to find out the internal resistance, you can have a you can utilize that equation. Let's come back to that point again. So let's say the terminal voltage which we are talking about, it is something like this, right? The I, let's say the I current is flowing, and we know what is the terminal voltage between these two, right? So let's say if it is R, so IR is dropped here, so it can be written as V is equal to the EMF epsilon minus, if the internal resistance is R, so it can be written as IR. Okay, so it would mean that you can write IR is equal to epsilon minus V, or you can write V is equal to you can also write V is equal to I into R. So now see, we are using here a resistor box, right? So we know the resistance, so we have to solve this equation in that term. So let's say what I do is that we utilize this this equation. If you write, so you can write it as epsilon this EMF is equal to V plus IR. Okay, so if I determine with this, what would be the epsilon by V? So if I get the epsilon by V, because that relation we have from the length one, so we utilize the similar form from here. So we can write epsilon by V, and that can be written as V plus IR upon V, right? And it would mean that 1 plus I upon V into R, and V upon I is equal to R, right? So here you can write 1 plus R upon R. Okay, right? So now I utilize this equation and this equation together, and then what I will get? I will get L1 upon L2 is equal to 1 plus R upon R. Now you solve for the internal resistance, you will get, so what you would get? You would get R equal to this will go here, so it will become L1 divided by L2 minus 1 and multiplied by R, right? So this is how, see, utilizing this potentiometer and finding the positions for the length from A, the L1 and L2, where you have a galvanometer reading once it is connected through cell, or the junction was also there. Now you see that how this circuit well utilized to find out even the internal resistance of the cell towards greater accuracy, right? And the good point is that it doesn't draw any current through the cell, because this is all where we are making the current flow through this galvanometer is 0. So this is a very good concept where you can have the understanding of this potentiometer and how you can utilize the Kirchhoff law to find even the EMFs of the unknown cells or internal resistance of the unknown cells using this conceptual theory given, and also that proper arrangement of the device and the circuit. So this is all about potentiometer. So this here we end the chapter, and we'll discuss about summary and some question answer in our next lecture. So see you there. Thank you.